Welcome everyone to Brandforsk and this result webinar. My name is Mattias Delin and I'm the research director here at Brandforsk. We are talking today about the duration of heating phase concept, literature summary and a roadmap. And with us today we have Robert McNamee from Lund University in Sweden and Thomas Janet from Johns Hopkins University in the US. Welcome Robert and Thomas.
Thank you.
Thanks.
Hello, everyone.
Yes, I can say good morning to you, Thomas, I think, because it's still morning
Yes.
in where you are. Yeah.
Good afternoon, Matthias. Thanks for having us.
Yeah. So first of all, who are you? Tell me about yourself, Thomas.
Yes, so my name is Thomas Janet. I'm an assistant professor in the Department of Civil and Systems Engineering at Johns Hopkins University in Maryland in the United States. And my area of research and teaching is structural fire engineering, including lots of numerical modeling of structures in fire.
Okay. Very welcome here today.
Thank you.
And Robert, who are you?
Yes, I'm 20% senior adjunct lecturer at the fire department of Lund University. And this project is under the umbrella of Lund University. And I have another life that is the 80% of my time that's at RISE as a research developer. And me and Thomas met in some international collaborations on this topic. So
yeah, good, very good. Yeah, welcome. We will see more of you in a while. You can present your project, but first of all, I will give some brief information about Brandforsk and this webinar. But I will see you guys later. And just a brief information about Brandforsk, if you are not already familiar with us. We have a vision, a fire-safe and sustainable society built on knowledge. We say that we develop and we communicate knowledge, and the development is, of course, mainly research, and the communication is, for example, this webinar. And all this is made to limit the negative consequences of fires in the society. And we started in 1979, and we are now a foundation since 2019. Everything that we do is funded by our supporting organizations. And this makes us a collaboration between many parts in the society. And last year we raised about 700,000 euro for this work. And this money are of course used to fund research projects like this one that we will hear about in a while. And also we work a lot with communication, the results of knowledge, so that you can use it. We also have a research school for practicing fire safety engineers, and we have scholarships for students. These are our supporting organizations so far this year, and we hope to see many more in a short while. And the fundraising also closing up to about 600,000 euros so far. So please chip in if you are not already doing that, or maybe add your contributions as well. The program here today, after this short introduction, we will have a presentation of the project. It's about 40 minutes long, and then we will have time for questions. And as I said earlier, please ask your questions in the Q&A.
welcome to this presentation on the topic fire resistance. We will present a complementary and more robust approach to evaluate fire resistance compared with the traditional standardized evaluation. The project is sponsored by Brandforsk and Lund University, with Lund University as main applicant. I'm the project leader and Thomas the main contributor. And maybe you noticed that the project title is not exactly the same as the title you see on the report to the right side in this on this slide. This is because we think that it's easier to spread the message, including the description burnout resistance, instead of just duration of heating phase. More on this later. This is the reference group of the project. As this is a quite small project, the activities with reference group was a first initial meeting to describe and get input regarding the concept. And in the end, all members have had the chance to give input to the draft of the report. We've got some really good input from the group. And now we are working on the final version of the report. The target group for the study is the whole fire community, as we think the concept we are presenting is a real step forward for the profession. The goal of the project is to create a platform for continuing the development of the concept. This is done by summarizing the existing studies and presenting a roadmap for further development. So, what is this concept I just mentioned? Let's start with some short description of how fire resistance is evaluated during furnace testing according to existing fire resistance standards. In the fire resistance test procedure, you evaluate the ability of structural elements to maintain a function when exposed to a prescribed heating scenario. These functions can be to maintain the load-bearing capacity, the integrity, or the ability to thermally insulate the fire on one side of the structure. These are 3 of the fire resistance classes that are followed by a number symbolizing the minutes that the criteria are maintained. Here you see the temperature development during a standard fire exposure and the evaluation of the criteria during 90 minutes. Directly when the criteria are broken, the test is stopped, meaning that the criteria are only evaluated during a continuous growing fire. This is important. You can see the system, the fire resistance evaluating system, as a system for grading elements or structures based on the hypothesis that the higher fire resistance time will perform better in a real fire. We will later in the presentation show that it's not necessarily always the case. So, there are different ways of evaluation of fire performance of an element. Either you can do a performance-based analysis of an element or a structure in a real building with realistic fire exposure that may be based on the opening factor, properties of the enclosure, and the real fuel load. This is very rarely done in practice. Usually the rating of elements is done in a more generic way before you know the final use of the element. Then you use the traditional fire resistance rating that I described in the previous picture, or you can, before knowing the final use of the element, determine the burnout resistance based on the duration of heating phase concept that we suggest. You don't need to see this as either a traditional fire resistance or burnout resistance. We see burnout resistance as a complementary robustness measure to fire resistance evaluation. So what is this burnout resistance and the duration of heating phase concept? When following the duration of heating phase concept, you determine the longest fire exposure an element or structure can survive when including a cooling phase. So the element is not allowed to collapse during the cooling phase. In this figure, you see elements that have a traditional fire resistance of 60 minutes. But when the demand is to also survive the cooling phase, the heating phase where it can survive the cooling phase also is only around 25 minutes. The point here is that different structures may behave very differently when also including the cooling phase. And as all fires include a cooling down period, we see this concept as a complementary, robust way of evaluating the fire resistance. I use the word complementary as it is not realistic to think that this concept can replace the usual fire resistance evaluation, but it gives a new tool in the fire safety engineering toolbox for designing more robust structures. I should also say that the temperatures followed are defined by one of the parametric fires in the Eurocode that closely follows the standard fire curve, but then also including a cooling phase. As you can imagine, this evaluation always includes some type of iteration to find the burnout resistance. These iterations can be done both experimentally or theoretically by calculations. Thomas will show more of both these ways of determination later in the presentation. So to present it in another way, a burnout resistance of 42 minutes means that the structure also survives the cooling phase if heated up to 42 minutes. If heated longer, it will collapse during cooling. So 42 minutes can in this example be seen as a point of no return compared with a standard fire resistance of 60 minutes when only evaluating the heating phase?
So to better understand why we propose a complementary measure to the fire resistance that captures the possibility of failure during the cooling phase, let us have a closer look at the effect of cooling on the structural fire response. As Robert mentioned, when characterizing traditionally a building element or structural member under fire, the characterization consists in heating up the member until failure, and that time is the standard fire resistance. Now the question is, what happens if we stop the thermal exposure on this element before failure? So let's say a column in a furnace, we would heat it up with the ISO 834 time temperature curve, but stop the exposure before the fire resistance time, and that would be followed by a cooling. But the load is maintained on the member. Well, during heating, the load-bearing capacity of the member decreases up to a certain point. But importantly, during cooling, the load-bearing capacity will continue to decrease. It will eventually reach a minimum value, and then it may partly recover or remain constant. But we have this delayed reduction in load-bearing capacity, which means that knowing only the standard fire resistance rating R, it is not possible to determine whether the member would survive a shorter fire exposure. That's not enough information. What are the factors that explain this continued reduction in load-bearing capacity? Well, in most cases, the governing factor is simply thermal inertia. In other words, the delayed heat transfer toward the inner parts of the section that continue even as the fire dies out, or in a furnace, the gas temperatures have peaked and start to decrease. Other factors include material-dependent properties. So in some cases, for example, in concrete, there is an additional reduction of strength during cooling, which is well documented and, for example, incorporated in Eurocode 4. There are also stress redistributions as the thermal gradients changes in the sections of the members, and load redistribution in structural assemblies under heating and cooling. You may think of connections in steel structures that become subject to tension during the cooling phase. As a result of these physical factors, failures in the cooling phase may happen for load-bearing structures. It's easy to show that numerically. Here on the plot, first you see the thermal analysis of a reinforced concrete section. If we subject a reinforced concrete section to the red time temperature curve shown there, we will compute the temperature elevation in different parts of the section. And you can see that in the center of the section, point C, the temperature keeps on increasing for hours, even after the thermal exposure temperature in the compartment is back to 20 degrees C. So if then we conduct the structural analysis and we load that member, we maintain the load constant and we run the fire, we can compute that depending on the applied load ratio, we may have some failures during the cooling phase or even long after the end of the fire. Failures in the cooling phase may happen. We can also show that experimentally, so not only numerically. I will say more on previous studies focusing on this phenomenon, but here is an example video from an experiment on a glulam timber column, which had a fire resistance of 55 or 58 minutes, two values because we repeated the test twice. So two identical specimens had that those fire resistance. And here the identical specimen was subjected to heating for 15 minutes of the ISO fire, followed by a controlled cooling. And what you will see in the video is that we are at about 2 hours and 30 minutes in the experiment, and the column will reach a failure under constant load. So again, these failures in the cooling phase may happen for the factors that we discussed before. And failures in the cooling phase have happened. This is also the motivation behind this work. So in real case fires, building fires, we have unfortunately observed these kinds of behaviors. these collapses can be particularly threatening, dangerous for fire service intervention, as well as for occupants that would not have evacuated. The factors that we mentioned that influence the sensitivity to delayed failure or collapse in cooling depend on the material and the structure. Physically, these are, for example, the thermal properties that govern heat transfer. So it means that this behavior that we explained with continued reduction of the load-bearing capacity during cooling, they will depend on the specific type of material and structural elements. So an element, number one, under a certain duration of heating phase, so natural fire with heating followed by cooling, may or may not survive until burnout. And an element number two, subjected to with the same standard fire resistance of 60 minutes. So the two elements here have been rated with the same rating according to the standard fire resistance approach. But this element number two may behave very differently during cooling. And in that case, element number two may fail, while element number one would survive until burnout. So the point here is that because physically the factors are material and structural dependent in terms of performance during cooling, the standard fire resistance rating does not capture these behavior in cooling, so it is not appropriate to assess the possibility of failure during cooling. We need another type of assessment, another type of indicator. Because two elements with the same fire resistance rating may have different vulnerability to decay phases. So this new indicator of burnout resistance that we propose can be established through calculation or through testing. In order to describe it, let's first compare with the fire resistance rating. So in case of fire resistance, we subject a structural member for the load-bearing capacity criterion to a constant applied load, and then we subject that member to heating with the standard fire curve until failure. And the time of failure gives the fire resistance rating. Well, in order to establish the burnout resistance, the idea now is to subject the same member with the same applied loading to successively longer fires until determining the longest fire that the member can survive until burnout. So you may picture that as running first a test on the relatively short duration of ISO fire followed by cooling. And if the column has survived, for example, then repeating with a slightly longer test until finding the fire that would result in failure. And the burnout rating, burnout resistance, is the longest fire that the member can survive until burnout. So, of course, practically, it would not be necessary to do so many iterations. One could, for example, imagine that for certain type of structural members that are critical, there is a minimum burnout rating that is required. And so one test would be run to verify that the member can survive that fire until full burnout. In a computational setting, in terms of numerical analysis, it is fairly easy, though, to implement this kind of iterative procedure and characterize any type of structural member in terms of both the burnout resistance rating and the fire resistance rating. In that case, numerically, for the burnout resistance rating, we simply set up an iterative procedure in which we subject the member to increasingly longer fires until we find the difference between the fire that is survived indefinitely until burnout and the slightly longer fire that result in a failure, usually then during cooling or even long after the end of the cooling phase. Importantly, in order to define a standardized rating and to be able to compare elements, we need to select some type of time temperature exposure and systematically use the same kinds of time temperature exposures. The same way as for fire resistance, we use the ISO 834 fire curve, for example, in most parts of the world. So what we propose is to use the Eurocode parametric fire, where the heating phase follows the ISO 834 curve, and the linear cooling phase is according to the parametric fire model. Why this model? It's because, well, there is a need to select one systematic model to always apply the same conditions to different members to allow comparison. And that specific fire has the advantage of being one natural fire that has been incorporated in the Eurocode. So in that sense, it has already been agreed upon in the fire engineering community. Some important points when running those analyses is that the simulations must be run for long enough, including the heat transfer analysis. And we will see for some members, this means hours, because really the temperature increase in the inner parts of the sections can take a very long time. Material models must also be appropriate for simulating the behavior during cooling, which means in many cases, irreversibility of properties. As I mentioned, this burnout resistance rating can also be assessed experimentally. This has been done in some previous studies that I will briefly describe. So the proof of concept has been established, including the fact that it is possible to control the cooling phase in a standard furnace with reasonable accuracy. And experimental results that were obtained in furnaces aligned fairly well with numerical predictions, including simulations done a priori, so which gives confidence again in the concept and in the ability to assess the burnout resistance. There have been a number of studies which applied this concept of duration of heating phase and burnout resistance rating over approximately the last 10 years. Some studies have been conducted by members of our group to further develop the concept and apply it to different structural members. And in other studies, also the concept has been adopted by other groups who applied it in their own studies. Many cases, this concept has been applied to reinforced concrete structures, but there have been also some studies on timber and a few on steel and protected steel members. I will now briefly describe a few of those previous studies. And in all cases, there are some references that I also mentioned that can provide further details on those studies. So first, numerical analysis on reinforced concrete columns. In a 2019 study, we collected 74 standard fire resistance tests on reinforced concrete columns, and we built numerical models by finite element method of these tests. So in a first step, we simulated the standard fire resistance tests themselves to recompute the fire resistance based on the model. The results are plotted on the screen. As you can see, the average agreement in terms of prediction versus test is fairly good at 0.95. However, there is a very large dispersion still, which indicates that it is still not trivial to capture all uncertainties when modeling standard fire resistance tests on reinforced concrete members. And in some cases, obviously, there are uncertainty in the models. In other cases, also, a same laboratory repeats an experiment of fire resistance test on two identical reinforced concrete columns and obtains quite a significant discrepancy. So there is also variability in nature and in the experimental process. All of these are reflected in this dispersion. Simply, it's important to mention and to recall that whenever we do one test or one model, there is variability, there is uncertainty as well, even though on average we are confident that we are capturing what's happening. So in the second step, we modeled those same 74 reinforced concrete columns with the iterative procedure that was mentioned to evaluate their burnout resistance. And the results are plotted on the right. As you can see, there was an almost linear relationship between the burnout resistance and the fire resistance. And the coefficient was around 0.7 or 0.72 between the burnout resistance and the standard fire resistance. It means that the reinforced concrete columns with a fire resistance of 90 minutes would survive a fire that lasts for 63 minutes or less until the very end of the fire event. But if the fire lasts longer than 63 minutes, the column would eventually fail during or after the cooling phase. Just the thermal exposure would have been such that the column has been damaged to such an extent that it will not survive indefinitely. It's important to re-emphasize that this burnout resistance is shorter than the fire resistance. That does not mean that the column would fail earlier than the 90 minutes. In this example, with the burnout resistance of 63 minutes, failure occurs later than 150 minutes. So here we are characterizing the ability to survive to full burnout. We are not characterizing the time of failure. So again, a column characterized with 90 minutes of fire resistance would fail later than 90 minutes when subjected to the ISO 834 curve. That is clear. So in those analyses, again, we looked at the factors that led to those failures in cooling. And again, the thermal inertia was identified as a key factor by looking at the temperature increase inside the sections over time during the cooling. Next, I present here an experimental study on reinforced concrete columns. So this is a follow-up of the numerical study that was presented before. The idea here was to test identical column specimens, reinforced concrete columns, in a standard furnace under different duration of heating in order to assess the burnout resistance experimentally. So here, 4 columns were tested in Liège University in Belgium. And you can see the column number 1 was tested under the standard fire resistance testing protocol. And then in test 2, the column was heated for 45 minutes, followed by cooling. Test 3, 55 minutes, and test 4, 72 minutes. The results are shown here. So the first test allows establishing the fire resistance time at 83 minutes for this column specimen. So R is equal to 83 minutes. That same column was able to survive the fires of 45 and 55 minutes. The columns were then loaded to evaluate their residual load-bearing capacity. And finally, in test 4, the column failed during the cooling phase when subjected to a duration of heating phase of 72 minutes. You see the evolution of displacements as a function of time on the right. And so the blue curve is for this test 4, where you have the end of heating at 72 minutes, but the column eventually fails during the cooling phase. So for that column, the burnout resistance rating is really between 55 minutes and 72 minutes. The column could survive the 55 minutes fire, but not the 72 minutes fire. So you see these experiments were useful as a proof of concept of the method, of the concept. It was possible to control the cooling phase as well as to get the different types of behavior of outcomes where we have a failure in heating, a failure in cooling, and a survival until full burnout. In that study, numerical modeling was used a priori before the test in order to inform the durations of the fires that we would apply in the furnaces. And then again, at the end, to compare the evolutions of deformations with time. And we found a good agreement with the numerical study that was conducted before and the experiments in terms of burnout resistance rating, as well as in terms of predicting a failure in cooling. Next, I will describe a study on timber members. So in that 2021 study, the procedure was similar to what we did on the reinforced concrete columns. We selected and compiled standard fire test on glue-lamp timber columns. We first modeled the standard fire resistance test with the finite element software, and then we simulated those same columns under the same loading conditions under natural fires to establish their burnout resistance rating. So on the left, you see the data from modeling of the standard fire resistance test, and on the right, the burnout resistance rating. For the timber columns, we see greater dispersion in terms of burnout resistance rating compared to the reinforced concrete columns. We also see a lower coefficient of proportionality between DHP, or burnout resistance, and standard failure resistance than for the concrete columns. This captures the fact that timber columns have a higher propensity of failure during the cooling phase compared to the reinforced concrete column. That's what the numerical models show. So why this vulnerability to failure in the cooling phase in timber columns? Well, as we explained before, the thermal inertia and the continued heating of the inner parts of the section is again key. This effect is pronounced in timber members because sections are relatively massive, if we compare to steel, for example, and the material has low conductivity. But another point that is really specific here to timber, it has to do with the mechanical properties and their dependency to temperature. Specifically, timber strength loss starts at relatively low temperature, and so this compounds the effect. What does that mean? If we look at the Eurocode 5 figure B4, which gives the strength reduction factor for the strength of timber, we see that in compression, the strength is reduced by 75% already at 100 degrees C. And 100 degrees C is a temperature that can be reached hours after the end of a fire due to the delayed heat wave toward the core of a section under certain conditions, depending on the thermal exposure. When steel or concrete experience temperatures of 100 degrees C, their strength is not yet affected or not meaningfully, but for timber, you see already a very dramatic reduction in strength. So this is an effect that we need to take into account if and when we require timber structures to survive until full burnout. And this effect has been well documented also by other scholars who pointed to this continued heating, very slow heating in the core of timber sections, including through thermocouple measurements in full-scale experiments. And you see some of the references at the bottom of the slide over there. And these scholars have also described this phenomenon combined and compounded by the strength loss at relatively low temperature for timber. Of course, in addition to that, there are effects from the fact that timber is combustible, and for example, smoldering can play a big role in stability or loss of stability under natural fire. But here, what I'm describing is really about the heat transfer and structural mechanics linked to the strength loss at those temperatures that are reached in the cooling phase. So this animation shows this effect of really slow temperature increase in the core of a section. So here we took a 28 centimeter by 28 centimeter timber section subjected to heating for 15 minutes, and then this linear cooling that gets back to 20 degrees after about 80 minutes. And you can see that the heat wave and this heating continuously for hours. Here we are 2 hours, so it's already compartment is back to 20 degrees C, but the core is still increasing in temperature, and we'll run this for 7 hours, and we see still slow temperature increase toward the core of the section. So complementing this numerical study, in 2023, with a consortium, we published results from experiments in furnaces on glulam timber columns. So these experiments were conducted at Braunschweig, and in this case, there were 8 identical glulam column specimens of 28 centimeter by 28 centimeters that were tested in the standard furnace. Each test was repeated twice, so we had a characterization of the standard failure resistance, which was 55 and 58 minutes for 2 specimens, and then 2 specimens heated for 15 minutes and 2 specimens heated for 10 minutes, all under the same conditions, except for the thermal exposure, so same loading boundary conditions. Here are the results. So as I mentioned, the standard failure resistance was between 55 and 58 minutes. And in the 2 experiments where the heating was maintained for 15 minutes, followed by the control cooling. The timber columns failed during the cooling phase. The failure was late in the cooling phase, so after the gas temperature was, I would say, lower than 100 degrees C. And then 2 experiments were conducted under heating for 10 minutes, and those 2 timber columns survived and then were loaded until failure to evaluate their residual load-bearing capacity. So these experiments allowed identifying different types of behavior, including failure during the decay phase. It's also worth mentioning that end of flaming had been observed in those experiments where the columns failed. So this was not due to continued combustion, although some smoldering may have occurred in at least one case, but there was a clear cessation of flaming and a failure long after, mainly because of the effects of delayed heating that we mentioned. Further experiments are ongoing to study timber columns in wood creep compartment fires, so which allow us to study the effect of different parameters, including oxygen content, ventilation, different cooling rates, etc. Here, of course, it is not possible to control the time temperature exposure to the same extent as in the furnace, but on the other hand, we can look at the ability to survive to burnout under very realistic fire conditions and cooling rates that are nonlinear and so on. And here are a sample of results in the table where you see, again, all those failure in the cooling phase and after the end of the heating that was usually in the order of 30 minutes, 40 minutes. So this behavior was also observed, and we are in the process of analyzing the data and publishing more on these experiments. Briefly, but more information is in the report. There have been some studies on steel members and the effect of different levels of thermal protection on the steel members. And roughly what we found is that the ratio between the burnout resistance and the standard fire resistance is of the same order for the protected steel columns as it was for the reinforced concrete columns. The report also discusses additional considerations pertaining to the concept. For example, the effect of selecting different cooling phases. As I mentioned, and for the reason I explained, those studies were performed with the Eurocode parametric fire and the linear controlled cooling. But some studies have started to look at the effect of selecting another cooling rate. Here, in this case, on the slide, still maintaining the linear cooling, but changing the rate of cooling. And this was a study sponsored by the American Concrete Institute. And on the right, you can see that the DHP, or the burnout rating, is influenced by the rate of cooling, especially if the rate of cooling is very, very slow, the burnout resistance rating would decrease. And then at some points, as the rate of rating becomes faster, it plateaus, and then there is less of an effect once it becomes a very fast cooling. But on this effect of cooling, we also have the natural wood creep fire experiments that I just mentioned on the timber columns. So here you can see the temperature time curves in the compartment with all those different cooling phases depending on ventilation and fuel and the fire dynamics. And the points or the dots on the plots represent the time of failure in all those experiments. So you see failure in the cooling phase under different types of cooling rates and cooling curves. So we will also study those to understand the relationship. But the key point here is that in our opinion, the parametric fire is convenient because it is already in a code. It is a linear cooling that is relatively simple to explain, to describe. And it's clear that it does not represent one specific real fire, but any fire curve, is specific to one specific compartment. Plus, we see this burnout resistance rating as an indicator that can be determined before we know the final use of a member. It would really characterize the member. It's not attached to a specific fire dynamics. So we think the key point is to select one type of fire that is always the same, that is applied in the same way.
So now we want to discuss some gaps and roadmap for future development of the concept. If we start with fire resistance testing, including the cooling phase. We have shown with some practical examples that the burnout resistance can be determined by furnace testing. But there are some remaining questions that needs to be solved when doing this type of tests on a more regular basis, or if writing a standard for these procedures. First, we have the temperature limits. In the figure, you see the temperature limits defined in the European fire resistance standard. We think it may be quite difficult to follow the cooling curve with the same precision as the heating curve precision already described. So we suggest that some more deviation is allowed during the cooling phase, but it must be on the safe side. This is also our suggestion regarding the allowed deviation of the area under the temperature curve. Also in the report, there are some discussion on the influence from oxygen content in the cooling phase that may be important for some materials. Also important is the duration of the experiment. When to stop? This criterion may be defined as a time, but that seems rather unphysical given the different behaviors that we have seen here in the cooling phase. Another option is to define it as an inner temperature criterion. But it is then it can lead to very long test durations. So this is very important topics to discuss when developing this context. And when talking about numerical investigations, to do precise modeling, we need to both improve our models as well as the material data and properties used for modeling. This is needed both for determining burnout resistance and also for real performance-based design of structures. Here are some examples from some recent work developing material data on concrete, and we need to put more effort to get better data also for mass timber. So some important research directions. Is there a better standardized natural fire to use? Or more importantly, do we want a better definition of the cooling phase? The cooling phase in real fires are never linear. And experimentally, we have the already mentioned duration of the test, but also the precision in the procedure. And regarding numerical modeling, when is it good enough? And is it possible to use a combination of testing and calculations? One example of this combination might be to extrapolate. If you do one fire test for a certain load level, and can you then use the numerical modeling for extrapolating to other load levels? This is questions to further develop.
So to conclude, in this report, we describe the burnout resistance as a proposed complementary rating or measure to complement the standard fire resistance. And this burnout resistance is defined as the longest fire that the structural member can survive indefinitely, when including also the effects of the cooling phase. It is developed to fill an identified gap, which is that structures may fail during the cooling phase for the reasons we explained and we described, and the standard fire resistance is ill-suited to capture this vulnerability. Previous studies have shown proof of concept that this burnout resistance rating can be determined experimentally, notably for reinforced concrete, for timber members that has been shown. Now, if we want to make it very standard and systematic and used throughout various laboratories, there are some additional details of the protocols or some additional considerations that should be refined and defined, as has also been discussed. And some suggestions are formulated in the report. One important example is the termination criteria. For example, simulations have shown that failure can occur many hours after the end of heating phase. However, if we are thinking about implementation in a laboratory, there will be some practical and logistic constraints in terms of the workday and so on. So some thoughts are needed there. Numerical modeling appears as a very valuable tool to study this behavior. Numerical modeling is being developed anyway to enable performance-based fire design, and it has become more common to simulate the behavior of building structures under fires with cooling or traveling fires, localized fires, etc. These models require appropriate models, for example, for the materials and how the properties vary in cooling. So all this knowledge can also be leveraged to implement in the context of burnout resistance rating. Finally, one aspect that we didn't cover in the presentation, but that is in the report, is discussing the behavior of entire structural assemblies when subjected to heating and cooling, because some of the load redistributions that occur during the cooling phase can also lead to some detrimental effects in entire structures during cooling. So this is an interesting area of further exploration to make sure that we can design buildings for overall stability and resilience under fire until full burnout. The question is open whether such a rating is the most appropriate tool to achieve this means, because we see this rating primarily as a qualification for members, the same way the standard fire resistance is. But that being said, there is much to gain in further studying of how entire structures can be designed to withstand fire until full burnout in a sustainable and resilient way. We end by thanking very much again Bransford and Lund University for the support, as well as the members of the reference groups for their great feedback, inputs, and support toward this project. It was a pleasure for Robert and I to collaborate, and we even had the chance to meet in person in Maryland last summer to work on that project. Thank you.
Thank you, Thomas and Robert. I will start with a question that I have myself. I was thinking about the fire service, for example, if they come to a building and it's been a fire and they put the fire out, but they are worried about, is there still heat in the construction? And you talked about the point of no return. Sounds very dramatic. But what if they try to cool this with water, for example? Is it possible to cool the construction with water?
Yes, thank you, Matthias. Maybe I can take that question, at least initially. So a couple of things here to mention. So first, theoretically, the phenomena that we highlight with the continued heat transfer and reduction of capacity during cooling. So this phenomena will be there, from the physics in any case during a fire. But it is true that the thermal exposure, including during the cooling phase, quantitatively that will influence whether we have more or less of a propensity of delayed failure. So specifically to your question, I do think that if the member is cooled externally, for example, through water spraying, that would lead to more heat losses, and so a lower temperature increase toward the core of the section, and so that would tend to be beneficial and maybe to reduce this risk of collapse. Now, I think that deserves further studies and depending on the materials and structures, etc. But for timber, Robert and I with others are working on some experiments, and preliminary results seem to suggest that indeed cooling the structure could be favorable.
Yes, we have some experiments of it. And also, of course, this, as Thomas said, of course, the physics during cooling, you stop the energy supply from the surface. But in some cases, you already have enough energy to redistribute. So it's always, I think it's a good idea. So that was what.
So please try that.
Yeah, please try.
Yeah. And what if the fire service use thermal cameras, for example, to try to see what is going on inside constructions? Is that a good tool, or what do you think?
So the heat transfer and the temperature is certainly, one of the key, if not the most important factors here. The challenge is that you really need to get access to the interior, to the inner temperatures, and it's really the delayed increase inside the members that will lead to this reduction of temperature, because the external part of the cross section, the perimeter, they peaked in temperature more or less at the time of peak gas temperature, when the fire is fully developed and peaks in terms of the heat that's brought, right? And then they start to cool off, but it's the inside of the section that will have this delayed increase, and that leads to a continued reduction, especially, concrete or timber, the materials are non-recoverable, so the perimeter remains damaged, and then the core gets also weakened, right? So the technology that could be useful to fire service would need to be able to pick up the temperature inside the section, and it's a pretty tough challenge because you have to account for the whole thermal gradients and whole transient temperature.
Okay. So.
I think also important when you're talking about this is that when we talk about the fire service intervention, the important thing also to remember is that there is also in all assemblies, structural assemblies, there are certain amounts of redistributions of loads and things. So this is not really linear, exactly this is happening. This is only one of the factors in the whole equation when you talk about rescue service. So then we're on this more structural level that Thomas talked about in the end. You can look at cooling in the structural level also when you have assembly. So
right, so they need to to have a lot of knowledge about the buildings and the constructions to do their risk assessment on site. I hope that you can set up a course at your university for them.
Yes, that's right. And Robert is right to point out the structural response. So we didn't show much of those results. Some of these are in the report. But if you take now a structural system, a structural assembly, because a temperature increase leads to thermal expansion, and you have some restraint effects, so you have redistribution of forces. And then during the cooling, you can have a reversal. You can have some members that get into tension and that pulls on other members. So this is quite complex, and you can have phenomena that are quite complex. And so we started to investigate this response during cooling, but there is a lot to unpack and to understand in order to assess once somebody gets into a building, how it's going to behave throughout this whole burnout phase.
Yes, thank you. You compared steel and reinforced concrete and timber, and you explained that this B is X times R. Do you have any general, amounts on this X for steel and reinforced concrete and timber, for example? Did you see any pattern in how they varied?
Yes. So based on our studies, numerical and then some experimental corroboration for columns, we are talking about loaded columns. For reinforced concrete, the factor is about 70%. So this burnout resistance was about 70%, 0.7 of the duration of the stratosphere resistance. And we have experiments and numerical results for that for concrete. For steel, numerical results, they were about the same range. We had between 65%, 75%, depending on the amount of insulation, but it more or less aligns. And for timber, results indicate that it's significantly lower. So the burnout resistance is varies now in the range between 25 to 50% of the fire resistance for the range of members that we studied. So we need always to be careful when we extrapolate, but we studied different sections, loading rates, etc. And we think we understand why it is lower for timber. If you think about this delayed heat transfer toward the core of the section, it means that when you subject a structural member or section to heating, eventually there will be some heating of the core of the section. But if the section is relatively massive, the temperature is not going to increase that much. You don't get to 600, 700 degrees C inside, the center of a timber or reinforced concrete section. You get to maybe 100 degrees C, 150. And if you look at the reduction of strengths of the different materials, for example, from the Eurocode, so you take test data, the behavior is very different for timber as opposed to steel or concrete, in the sense that steel or concrete, you have originally a plateau, from the ambient temperature to 200, 300, depends if you're talking about concrete or steel, there is no reduction. The effects only come later. But timber strength starts to decrease almost immediately. And for compressive strength parallel to grain, the Eurocode 5 says that at 100 degrees Celsius, timber compressive strength is only 25% of the initial compressive strength. So when you think about this delayed heating, even if the core only gets to 80 degrees C, 100 degrees C, that leads to a reduction of strength with timber. So that's a challenge that we are working on to fully understand and see how, in terms of design, we can overcome that to make sure that timber structures can also survive to full burnout.
Yeah, that's really interesting, and I think, and we have had concrete buildings, for example, for quite a long time, and so if we consider reality as a full-scale experiment, we also see that we don't have collapse very often, but it does happen, but we don't have so many timber buildings yet that have been exposed to this stress of severe fires so far. So now this is really interesting, I think. I was thinking about a lot of people, I think, are concerned today about sustainability and the sustainable development of our society, and timber buildings are a really hot topic. And what are your thoughts on how to use this knowledge, to get sustainable buildings that withstand at least most fires that they can experience during their lifetime?
I can say two things about this. First, it is that if you talk about timber buildings and fire, if we learn more about the real behavior of timber in fire, then we can build in a way that is more safe. And if it's more safe, we will have more confidence in building it, and we will avoid these spectacular fires, because that's one of the biggest challenges for timber, is if there is some spectacular fire, because the regulations and the community is very much reacting on big catastrophes. It's driven like that. So that's a risk for building with timber. And then we have the second thing is that if we make tools that is more precise and better in predicting something that is closer to the real behavior, then we can, in a confident way, have different levels of safety, and we can actually, in a lot of cases, because we have a lot of over safety also actually. So if the tools are good enough, then we can be confident to have reduced cross sections in some places and have less building materials. That's also in the sustainability, under the sustainability umbrella. So.
All right.
Yes, these are great points. I would say, so I will just reinforce the first thing that Robert said. I think is key is sustainability has to go with safety, and if something is not well understood and not well designed, as there are more and more of such buildings, so a new solution is implemented at scale, the probability to have a big fire increases just by nature if there are more buildings. And if things were ill-conceived, then that could lead to a backlash to regulation, and in the end, you can't implement those solutions anymore. So that's really not a desirable outcome. And I will say also, so this, understanding ability to survive to burnout and this concept, we are not saying that necessarily it applies, across the board to all buildings, all situations, right? I mean, there is always the idea of some importance class of different buildings, and what is the target when we design for low probability events such as a fire. So many buildings, as long as people can evacuate and fire service can fight from from outside, maybe it's not a big deal if eventually they collapse. But when we are going to taller buildings or inside cities, etc., it's very important to understand whether they would collapse or not, or to design them so that they don't collapse. So in terms of the entire building stock, we're not talking necessarily about all buildings. And then when we design a building, maybe we don't need to have all individual members being, surviving to burnout. Once again, what we want is overall stability. So I think we can devise sustainable solutions where use of the materials, the resource is still very rational, but important buildings are strengthened where it's needed so that we avoid a disaster and we have this resilience built in.
Yeah, very good. So if I want to order a building today or tomorrow, and I want it to withstand a burnout, for example, is it possible for me to communicate that and actually get a building like that? Or do you have to develop more tools to actually communicate and order a building like that?
So I think with, methods are not perfect and not perfectly mature because we would like to have some more knowledge about, for example, the material properties in cooling, but there is reasonable correlation with our modeling, finite element modeling, and some of the experiments that are coming out. So I think it's possible to apply finite element modeling with some conservativeness and get a sense of the design that would withstand the fire, including the cooling phase. With timber, it's a very complex material in fire. There is lots of research going on, and some of the aspects we didn't discuss that much are more related to the combustion or the smoldering, for example, that can happen during cooling. So we are not claiming that we can predict or model all of that yet. Certainly, there is more research needed. But capturing this delayed heat transfer, these structural mechanics, we are starting to really understand better that, and we can have some models that certainly inform the design for that.
And also this combination of modeling and fire testing. If you have your model and then you pinpoint in what area you think you are, and then you can have a validating fire test. That's one way of doing it. So there are a lot of variants, but you can do these things, but it's not in any regulation.
No.
So it's not like you can look at a manual or a standard, but it's fairly. I think this concept is fairly simple, and I think that's good.
Oh, very good. Yeah. So what I have to do is really to define the design window in a very proper way to communicate what kind of building is it that I want to have. Yeah. Okay. Well, we have some more work to do. Any advice from you to the audience on how to use your report and this knowledge, for example, and something like that?
Well, I would say even if, with, for example, because we are on the topic of timber, but even more generally structures in fire, still, these are complex issues. And so even if the report does not provide all the answers, I hope it helps raising some of the questions, right? And I think when we are looking at innovative design, things that have not been tested that much by return of experience, as you were mentioning, Matthias, if you are building multi-story timber buildings, it's important to be curious and maybe not stop at the standard fire resistance and fire resistance rating systems that were devised decades ago for another type of purpose, and really be inquisitive and understand what would happen in case of a real fire and what the consequences would be. And then we can, engineers can look at the current knowledge to try to mitigate and find solutions and so on. But at least interrogating the expected true response in a fire, I think is really important.
Oh,
maybe.
Robert, any thoughts?
I agree totally. It's I think it's a good summary of it, actually. Good.
Yeah. Oh, well. Excellent. Very good. I think it's really interesting. I hope that you are you going to. What's your next step with this? Are you planning any more projects?
So we have an ongoing collaborative work with Robert and other partners, which has been very fruitful, focused on timber, and we've mentioned some of these during the presentation today. So there are more full-scale compartment fire tests ongoing. So these are really providing very valuable data. These are, some of the first tests where the timber members are loaded during the fire, and we have these natural fires. So measure temperatures, deformations, and so on in cooling. So that provides great data. We improve our understanding. We are also oriented toward finding solution, not only showing this vulnerability, but understanding how we can design any type of structures, and particularly maybe timber, to withstand fire until burnout. And we do some work with numerical modeling too. So we want them to translate this finding and this knowledge into tools and methods for software and simulation, so that engineers can design under realistic fire conditions.
That's also going on now. But one thing that will be discussed more in the future is what type of standards or how can you put it in a framework in a better way? We have presented a framework here, but I think it would be good if we start spreading the word, and then we talk more about the framework that we can have together, and then you naturally come to standardization.
Okay, yeah. Sounds wise. Yeah. Thank you very much. This is really interesting, and I hope to see you soon again in new projects. And spreading the word about this. So thank you very much. I will give some more information to the audience about upcoming webinars. But nice to see you here. Thank you.
Thank you, Matthias. Thank you to Branch Plus for the support.
Okay, some short information from us here at Brandforsk. I always want to remind everyone about our fundraising work, and everything that we do is funded by this fundraising. So please chip in if you are not already a supporting organization. There are different ways, and you are of course welcome to get in touch with us to discuss that if you are interested. And we also have a large number of webinars this winter and spring, and actually every week right now. And the next 3 are all in Swedish, but I hope that you can understand enough, even if you're not maybe fluent in Swedish. And we will talk about the reuse of fire safety products, for example, and also experiences from sprinklers in cultural heritage, and also an evaluation of escape places for people with different disabilities. We also have a podcast that is also in Swedish, so you can learn a lot about fire safety and also be fluent in Swedish after a couple of episodes, I think. And I would like to thank my colleagues, Francis Irinius and Matthias Hamrin, that is also working with this webinar, but behind the camera, so you actually don't see them, but they are doing a great job. Thank you very much. So thank you for listening, and please use this knowledge, and in that case you will actually add more fire safety in the society, and that is our vision. So please use it, and please spread the word. This webinar will be on our webpage and on our YouTube channel in about a week. So thank you. Bye bye.